this. Okay, so label the following species as aromatic, anti-aromatic, or non-aromatic. So what I like to do is always draw out the electrons in this case, so it doesn't confuse people, right? So here you have a lone pair, right? In case you guys forget, right? Nitrogen's supposed to have 5, so it's 1, 2, 3, 4, and 5 from each bond. 3 from a bond, 2 from the lone pair. Look at this nitrogen, it has 3 bonds, therefore it has 1 lone pair, right? Lone pair is here, right? And then a lone pair here, and a lone pair here. Okay, so let's start with the first one, right? So you have, let's, yeah, it's got to use the same color, but that's fine. So you have this pi bond, right? You have this pi bond, and you have this pi bond, right? So those are part of the ring. So first of all, it's a ring, right? It's just that 2 atoms happen to be nitrogen. That's okay, right? As long as it's a closed ring, right? Next thing is the p orbitals, right? If you looked at this in like a planar view, right? So we had a bond here, and we had a bond there, right? So we know there's p orbitals at this carbon-carbon bond. Same thing happens for nitrogen, right? It has a pi bond, right? That means that pi bond is coming from p orbitals because that's what pi bonds are. They're like slightly overlapping p orbitals, right? So this p orbital is being used, right? And I'll get into electrons later. So we have a total of 6 or 10 pi electrons in this case. This is a question to everyone here.
10.
So we have one answer, 10. Everyone else agree?
Yep.
Okay, that's wrong. That's fine though. So this is why I said understanding what a p orbital is and what it's doing is important. The p orbitals in nitrogen here, they're being used for that bond, right? So those electrons, right, they're lone pairs, but they can't be in p orbitals, right? So whenever you see a nitrogen system that has like pi bonds with the nitrogen, just think of it as a carbon, right? Yeah, it has a lone pair on its outside, but that's fine. But its p orbitals are being used as part of the ring, right? So the only electrons in this case that count as pi electrons, right, will be the ones from the bonds, right? So you have 2, 4, and 6, right?
Yeah.
These will be in what kind of orbitals? You guys remember?
sp2.
Yes, right? So the hybridization of the nitrogen, because it's participating in a double bond, right? That means, oops. These will be in a sp2 orbital that is perpendicular actually. So if this is a nitrogen here, we kind of make that clear, right? This orbital is coming out like this way. So it's perpendicular, or I guess that would be perpendicular to, it's outside the ring though, right? So the electrons are kind of just chilling out here in that orbital, but they're not participating in this aromatic ring cycle, right? So it has 6 electrons. Does that fit the Huckel's number or anti-Huckel?
Huckles?
Huckles, right? So what does that mean this compound is?
So it's an aromatic.
Yep.
Can you please explain the rule again about the electrons being on the outside?
Okay, so that has to do with what? Sorry, what are you saying?
Sorry. Because I don't remember if this was from like the group study like that we did on our own or from class, but basically if the electrons don't contribute to resonance, they count or something like that.
So this all has to do with the hybridization theory, which is why he goes over it in the first lectures of class, which in my opinion, you guys should be taught in Orgo 1, but they don't really even have a proper chapter in this textbook about it. But Bisco always loves talking about it because he knows how important it is. So things will not have a static hybridization. Hybridization, as he mentioned in his lecture, probably, it's all about the angles, right? It's literally like why things do, like they act in a certain way, just to get the proper angles, right? He probably gave you an example with cyclopropane, right? And he said that this has like kind of what's called banana bonds, and it acts as sp5, even though everything is sp3, right? And it has to do with like the p character. Well, it's kind of similar thing here, right? Is that things can shift out of sp3 or sp2. In this specific case, right, nitrogen, if we just looked at nitrogen, right, forget what it's bonded to, right? It has, this will be the rest of the structure. This will be the rest of the structure. It has a single bond, right? And it has a double bond here, right? So that means it's participating. If it's participating in a double bond, it's p orbitals, right? You could represent the double bond as this, right? So if they break open where electrons are delocalizing between them, right? That p orbital is being used, and it's being used within the ring, right? Which means that lone pair, right, has to be in a sp2 hybridized orbital that's outside of the aromatic ring, right? So when you're looking at lone pairs, basically you could check two things to determine hybridization. First, does it have any pi bonds? If it has pi bonds, whether it's a carbon or a nitrogen, that means it's sp2 hybridized, right? Because it's participating in a pi bond, right? And then that means the lone pair are in a sp2 orbital, right? Because if it's sp2 hybridized, the lone pair has to be in a hybrid orbital outside of it, right? And then you have cases where, like this oxygen, we'll see, well, maybe not in these examples, but sometimes to prevent becoming anti-aromatic. What's a good example I could give of that? So here, because this example isn't here, but I have some extra space. Well, I can erase it later, so that'll be fine. So if I draw this out, double bond here, 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 right? And let's do two examples of this. We have this, we have this. So these are similar enough systems, right? Where you have a oxygen ring, right? One's a 5-membered ring, the other's a 7-membered ring, right? And they both have their lone pairs, right? And this is where, like, what I mean that things can change their state of hybridization. You're gonna find here, right? It's gonna be sp2, the oxygen, right? And here it's gonna stay sp3, right? And all has to do with the rest of the electrons in the system, right? So first we can agree these are both closed rings, right? And then at every other carbon here, we have p orbitals. P orbital, sorry if they're weird drawings, but so in this one, just from the pi bonds, this one here, that one I drew the arrow, how many electrons are coming from pi bonds here?
4.
4, right? How many electrons are coming from pi bonds in this one?
6.
6, right? So we have 4 and 6, right? So this oxygen, right, it has a choice in both of these, right? If one of its lone, so both of its lone pairs can't be in a p orbital, right? Only one can be, right? Because that's just how orbitals are. They can only accept a pair of electrons, right? So never do that where you have two pairs of electrons. You're trying to count them both as pi electrons. That is literally never possible, right? It's always going to be one or not, right? So in this case,
Can you please say that again?
So when you have, I guess for the most part, it's usually on oxygen, maybe in some cases nitrogen. But when you have heteroatoms like oxygen and nitrogen with 2 lone pairs, both lone pairs are never in a p orbital. Only one can be in a p orbital, right? So in this case, right, we can, let's say we have one pair of the lone pair or whatever. Let's put it in a p orbital, right? Now, what does that make the total number of pi electrons here? 6, right? Because it's a pair of electrons. We already had 4. Now we have 6. So what does that make this molecule?
Anti-aromatic.
Aromatic.
I mean aromatic.
Yeah. So this is aromatic. This is what is this? I forget if this is furan or tetrahydrofuran. I think this is furan. And this one here, right? Let's say we put one of the lone pairs in a p orbital, right? How many electrons will we have now?
8.
8. So what does that make this? Anti, right? So if this was sp2, then one lone pair would be in a p orbital and the other orbital is sp2, right? So that's why the hybridization of this oxygen on this molecule on the right, right, is a sp3 because it's going to rehybridize as sp3. Because if this was sp3, what does that mean for this whole molecule? What will it be?
Non-aromatic.
Non-aromatic, right? Because at this point, you have lost your planarity, right? There's no more p orbitals at that point, right? So this is kind of the key. I feel like a lot of people always have issues is when to put electrons in the pi system, right? So when you're turning something anti-aromatic, things are going to want to stay sp3 because being non-aromatic is more stable than anti, right? Anti is the most unstable form. It's very high energy reactive molecules. Nothing wants to be anti-aromatic. So if things can rehybridize in a way that prevents it, they will. So that's why the oxygen here is sp3 and not sp2, because if it was sp2, right, one lone pair would be in a p orbital, and that would make this entire thing anti-aromatic. So instead, both of them are in sp3 orbitals, and then you have two other bonds. But here, in this case, you're going from, so if this was sp3, right, this oxygen, man, I really wish I had different colors. So wait, hold up. I think this should be it. There we go. There we go. All right, perfect. So this oxygen here, the one that I circled blue, right? Let's say it wasn't sp2 and it was sp3, right? What would make this, what would it make that molecule then?
Non-aromatic as well.
Non-aromatic, right? But it has an opportunity to become aromatic. And that's why it hybridizes to sp2, because being aromatic is more stable, right? So in general terms, right, you could say, like, let's actually put this kind of towards the middle. You have aromatic compounds. This is in terms of stability. This is just a very broad generalization, but they are more stable than anti. And sorry, done the wrong way. You have aromatic, you have non, then you have anti, right? And it would be decreasing stability here this way. So the most stable are aromatic, then non-aromatic, and then anti-aromatic, right? So that's the general trend. So whenever you're having issues of whether to determine if electrons are going to be part of your pi system or not, just think of what happens. Like first, you know, count all the other electrons and then see if you added two more, what would it do? It makes it anti, right? It's going to stay sp3 to prevent it from being aromatic at all. If it makes it, what's it called? If it makes it aromatic, then it's going to be sp2, right? So that's the kind of thing with the hybridization in these questions, how you can determine whether our oxygen is going to be sp3 or sp2, right? It all depends on the rest of the electrons in the ring, right? Probably go over practice problems with those like hybridization tomorrow, but this is just to explain this question at hand, right? So now let's start with this second molecule. So the first one is aromatic. Let's do the second one, right? This should take only a second to really even, you just look at it fast, you could tell me the answer without even doing anything.
It's non-aromatic.
Yeah. Why is it non-aromatic?
Because the top is sp3.
Yep. So this is a carbon bonded here. There are no p orbitals here, right? If you made this a carbanion, then technically it will actually, it would just become anti-aromatic, right? But if I made this, what is it? Positive charge, there we go. Then what would it be? Anti or aromatic?
It would be
Aromatic, right? 4n plus 2. In this case, n is just 0, right? So 2 pi electrons. And everything here has a p orbital, right? But as it is right now.
That's supposed to be anti, right?
No, 4n plus 2 corresponds to aromatic, right? So if this n was 0 here.
Oh, okay, yeah,
right?
yeah, I know it's aromatic.
Yeah. And if you had 4n, then that would mean 0 electrons, right? Okay. So this is non-aromatic, right? So as soon as you see any sp3 carbon or any base, like if you get lucky and it gives you a chain, automatically non-aromatic. Okay. Okay, so this is called the Cyclopentadienyl Carbocation. This one, it comes up a lot. It's a very good like synthetic molecule. I mean, it doesn't exist in nature, just people figure out a way to create it. So let's look at it. Does it fit criteria 1?
Yeah, cyclic.
Yeah, and the thing is, can you change the hybridization of this carbon?
Yo, the resonance.
Um,
Mm.
Technically, yeah. If you think about it, you could resonate it, but just makes the same structure, right?
Yeah.
So resonance doesn't really do anything in that.
So regardless, the carbocation will be a sp3.
It's going to be sp2. It's carbocation, right? Remember carbocations, right? Positive charge means they lost electrons, which is from another bond, right?
Yeah.
And what is the geometry of a carbocation? Is it tetrahedral, trigonoplanar, linear?
Forgot.
It's trigonoplanar, right? So a good thing to remember is they're sp2 hybridized, right? So it's always planar. So remember when you guys did like SN1 reactions with carbocations, you'd form racemic
I guess I was
mixtures.
thinking about it in the organic chemistry way. I was counting the three sticks, and I was like, oh,
So what I always do is I draw it out,
yeah.
and then you'll see if it's on a plane. I mean, actually, no, that's not a good way. Just look at the electron domains, right? So the plus side indicates that it lost a pair of electrons, so that means the other bond not shown. There's only one hydrogen here,
Mhm.
right? So it has 3 electron domains, right? So the way you could determine the hybridization based off that is sp2. You have 1 s orbital, 2 p orbitals.
Oh yeah.
3 electron domains,
Yeah.
right? So sp3 things have 4 bonds. Sp things have 2 bonds, right?
Yeah.
So this one is sp2, but it can't hybridize to sp3 at all. It's stuck like that. And we know that this is planar. And basically what you could always think of carbocations are, right, is don't think of them as a positive charge, right? They're really just the source of an empty p orbital, because that's all that's really happening, right? Positive charges aren't really positive charges. I mean, they are, but like really in organic chemistry, it's best to think of them as empty p orbitals, right? Because that's what happened. You broke a bond, right? It made this molecule flat at this point, and now you have an empty p orbital that can take electrons, whether that's a nucleophile or a base or whatever you might be doing. Actually, mostly nucleophiles, but it's just an empty p orbital. So we have an empty p orbital here. We have 2 being used here and 2 being used here, right? So you have how many pi electrons in this system?
4.
4. So what does that make this?
Anti.
Anti-aromatic. Okay.
Yeah.
So this one, I'm not gonna spell it out for you guys, but if you guys just look at it.
It's cyclic. Let's see.
This is an for the O, right? The fourth one.
I would say
Yeah,
it's
fourth one.
aromatic.
It's an aromatic.
Aromatic. And what's the hybridization on the oxygen?
sp2.
Right, because one of them you could put in a lone pair, then the other one would be in an sp2 orbital, right? You have 6 electron system. I mean, we kind of did it there too. So then you fit criteria 1 and you fit criteria 2 for aromaticity. This is aromatic. And now the last one's a little tricky, but like I said, just think of what is a pi electron, right? Just be careful of that nitrogen. But like I said, if you treat them all as carbons, it's even easier to see.
I would say it's aromatic.
Okay. How about you? Who's in there? Serena and Camille.
I wasn't doing it. Sorry, I was writing something down.
Okay, no, you guys can take a few moments to do that.
The lone pairs on the nitrogen can move. They can stay outside.
Oops. But yeah, right. So nitrogen is in a pi bond, right? So that's pi electrons are already in the ring. So that has to be sp2. And then that means there's 2 electrons here, 2 electrons here. So if this was sp2, you'd have 2 more electrons, right? And it would be aromatic, right? So that one is aromatic.
Oh, so just as a rule of thumb, when we have either oxygen or nitrogen with the lone pairs, if it already has a double bond on it, that means it's already like kind of locked in the p orbital, and whatever we see is the lone pair, right?
Yeah, so that just yeah, like that's actually a perfect way of thinking of it. But even more briefly, that means that it's pi electrons are already part of the system. That those any lone pairs on it are outside the ring, right? So I don't know if you'll see oxygen too much, not in this class. I mean, they are like people create oxygen synthons essentially, I used to work with this back in 2019.
And then
We
the lone
ended up-
pairs can't come down, they will just stay outside.
Yes, I mean, this is a simple system, but like CO minus is gonna come here, it's gonna kick back there. This was a positive charge, but you generally don't see too many double bonded oxygens. But yeah, whenever you see that nitrogen, and in the rare case you do see an oxygen with a double bond, its pi electrons are already part of the ring. Any other lone pairs, not part of the ring, right? And then in terms of making sure the hybridization is right, that was what I did down here, right? Making sure it's more stable. It's all, like I said, I don't know if any of you guys had me for Orgo 1, but like one of the first things I always start off with is that nature prefers the lowest state of potential energy. Right? That's true for physics, chemistry, biology, everything, right? It's just the way nature is, right? Things are constantly moving to a lower state of energy, right? Same thing happens in all these molecules, right? If things can go to a more stable state, they will. So things will rehybridize to either go from non-aromatic to aromatic, or from anti to non-aromatic, right? So that's the kind of notes for hybridization, is when it changes, it all has to do with how many other electrons are in the system. Oh, it's in draw mode, that's why. So, is there a way to fast erase? We could do, yeah, we'll be able to do question 2 as well, and probably 3. Yeah, 3. You should be able to do 3 as well too. Okay, let me see if I could like do a quick erase.
There's a back button.
That's gonna remove a lot of stuff from above. I think I could do this. Huge. So I like the OneNote. I mean, I guess I could have imported the PDF. Oh well. Next time. Yeah, your guys' first exam is in it's not in Marshak, by the way. I mean, I think he'll probably send you an announcement. They already have the rooms up because I signed up for proctoring for that section. It's gonna be in the Baskerville Hall.
It's so funny because I'm a Chem TA
Mhm.
and I got the email about the proctor thing and I
Yeah.
saw my
Yeah.
exam on there. I was
Yeah.
like,
Yeah, no, there's somebody who signed up for like every section. I was like,
Mona
damn.
Lisa, I think her name was.
yeah, I don't
I saw
know.
that name.
I was just like, damn, literally signed up
was
for
funny.
everything.
It was funny because like I saw my own exam, like my class. I was
Yeah.
thinking, why didn't I just put my name down there?
Yeah, that'd be funny. Okay, go back. Okay. All right, so rank the following dienophiles from least reactive to most reactive in a Diels-Alder reaction. So, water. I think someone asked this in the.
It was me.
Was you? Okay.
Yeah.
That's funny, but
I
go over it.
understood like when you explained it.
Mhm.
But I guess my confusion is like with the whole like the MEO and the CH3. So
Right.
I guess because that one's farther, it's like, is that one for the third molecule? Or do you want to explain it first before I say anything?
Well, I'll explain that part as I go. over
Okay.
it. So dienophiles, right? By definition, right?
I think it's still in eraser mode.
That's why this Zoto app. I mean, the app is great for PDFs. It's not good for writing.
What is this called? What kind of tablet is this? This actually looks pretty cool.
Surface. I've been using it for like 2 years. Literally, I don't use a notebook anymore. I just have like.
Yeah, it's actually really convenient to have.
I mean, you can do it on any 2-in-1 laptops, like other companies make it. But yeah, I have like my entire notebook for like the last 2.5 years now has just been on an online notebook.
Yeah, because it's and you could type on it too, right? You can attach a keyboard.
Yeah, it's the keyboard.
Oh yeah, that's pretty cool.
Okay, back to that thing there. Yeah, I mean, anyone who has like a tablet or whatever, if you use OneNote, like whenever classes are back in person, you could press the record button, right? And then you could record your lecturer talking as you take notes. And then when you finish recording, when you go back to your notes, if you press play, it will play it and tell you what you were writing at that time. So that's OneNote on any computer that you use. So even if you type notes through it, it'll still do the same thing. So I used to do that a lot. I have a lot of like recordings. So then like I could go back to my notes and
No,
hear
actually,
what
I
it
actually need
was.
to write all this down. This is actually my
Yeah.
cool show. You said this is called Surface.
No, so it's not on this computer. This app, OneNote, anyone can use this, right? If you get this, City College gives it to you for free, right? So
Yeah.
if you use OneNote and do your note taking and have like the recording going on at the same time, it'll literally like sync it up with your notes.
Yeah, I know this is because you could also write and type at the same time, right? You can with your keyboards. This I want to know what the device is. You said it's called
This is Surface.
Surface. Just I
Yes.
could just search up Surface and then
Yeah,
this will pop up.
Microsoft Surface.
Okay.
Okay, let's go back to Zoe. Anyways, so dienophiles by definition, right? They're diene lovers, right? That's what file means. You all know a lot of words with the word file in it. So they're searching for a diene, and they're things that are electron deficient that you guys saw in the Diels-Alders reaction. Did you guys do 2 + 2 additions as well? Like something like.
No. Wait. Yeah. Yeah. It's like when the arrows were like.
Yeah.
That will happen, right?
You even went over it Saturday with us.
Well, no, as far as I know, I only did 4 + 2. Because he said he's not going to do what's called electrocyclic reactions.
Oh, I think he went over like a general example in class and he was showing us why like that doesn't work.
Yeah, so that's called like what the things are like thermally allowed or something like that.
Yeah, with heat and he's with H nu and like you can like change the.
Yeah, you could excite the energy.
Level.
Essentially, whether things are thermally allowed or you have to photochemically excite them. Right?
Yeah.
That all has to do with. I'll probably go over that tomorrow. I have to check his syllabus. He said it wasn't on it, but I think the thermally allowed, like it's called dex rotary movement, con rotary movement. But anyways, let's get back to this. So dienophiles are things that have excellent lumos, right? And good lumos, like if we did let's do a basic diene, right? Let's just do alkene, simple ethene. Alkene, whatever you call it. I forgot the name. So this has 2 molecular orbitals, right? And this one should be pretty simple. Yeah. For every, I guess p orbital or atomic orbital in this case, you get a molecular orbital. We have 2, we're going to expect 2 MOs, right? And the other one, the phases will be opposite. Actually, tomorrow I'll go over how to like do this for a larger system.
No, he went through that the whole entire lecture. He was showing us.
Oh, so okay, you guys have so then we'll just do practice problem with it then. So this has 2 electrons, right? So this is the HOMO, this is the LUMO, right? So in general, right, whatever your alkene is here, right? When you start adding electron withdrawing groups to this, right, what this does, it lowers the gap between the HOMO and the LUMO, right? Electron withdrawing groups, right? They have a really good effect on basically lowering this gap. And then this kind of gets more into details, I guess, technically, like, quantum chemistry when you deal with like molecular orbitals like this, right? But when you have this decreased gap, right, it has more affinity for like HOMO-LUMO interactions, right? So there's like things like that are technically electrostatic, and then there's like HOMO-LUMO interactions, and then like there's a bunch of stuff like that, but that's like a master's level stuff. All you guys need to know is that electron withdrawing groups lower this energy level, right, for the LUMO. And for the LUMO, you want it to be as low energy as possible. And for HOMO, it's the opposite is true. So which is why you see generally on dienophiles, to make them very reactive, you get electron withdrawing groups on them, right? Because that lowers the energy level for this LUMO, because think about it, this is already an empty, molecular orbital, and now you have something that withdraws electron density from it. So it's pulling that electron density even more, right, which lowers its energy level. For the opposite is true if you have an electron donating group, right? That's going to increase the effect, like increase the energy level of the HOMO, because this is already electron rich. And now you're adding groups that are pushing more electron density there, right? So generally for dienophiles, good dienophiles have excellent electron withdrawing groups. Good dienes have excellent electron donating groups.
You said good.
I'll write it here too. Good dienophiles.
Excellent.
EWG, right? Good dienes. Electron donating groups, right? Because the dienophile is electron poor, and you're trying to make it even more electron poor, which is what electron withdrawing groups do.
Electron donating group stats?
Yeah, EDGs. So in chapter 18, you're going to learn all the most common ones. That's why I was saying the structure for the Klein textbook in hindsight is, I mean, it's a good textbook, but
Electron,
that's what it is. Donating groups,
neutron,
right? So
groups, decrease. One more.
yeah, so it lowers the energy level of the LUMO. And yeah, so these are all dienophiles, right? So essentially the way we could think, so once again, you got to kind of make sure you understand what this means. Most reactive, right?
Mhm.
What does that mean?
I'm just gonna
In
guess
terms
right
of
here.
energy, will it be high energy or low energy?
It'll be low energy. But if it's like reacting a lot, it won't take.
Well,
that
when
much
it
energy.
reacts, it'll become low energy, sure.
Oh,
But whether it's in a reactive state has to do with high energy, right? Because the higher your energy level, the more you're trying to get rid of that energy, right? Remember I said nature prefers the lowest state of potential energy. So as you lower your potential energy, you become more stable, right? So stable, you can correspond with low energy, right? Unstable or reactive, you correspond with high energy, right? So like I said, with electron withdrawing groups, right, the whole purpose is to decrease the energy level of the LUMO, which makes this entire thing more reactive, because the whole way it works, right, is the HOMO-LUMO interactions.
wait, decreasing gap.
So just write, if you want to write something on decreasing the LUMO energy level makes dienophiles more reactive, right? So the better electron withdrawing groups we have, the more reactive the
It makes dienophile more reactive.
yeah.
Okay.
So now we could start looking at all these kind of electron. So he said so now order them from least reactive. So you could think of this as, I guess, in this case, right, you could think of this as low energy or most electron rich, right? Because what did we say? Dienophiles want to be electron poor or electron rich?
Electron poor.
Yeah. So in this case, least reactive
reactive.
means it's electron rich, which would mean it's not very reactive because it's trying to be electron poor, right? And most reactive in this case would mean it's most electron poor, right? So that's the kind of key. If you were asked for dienes, the opposite is true. Less reactive dienes, less reactive dienes, right? They will be electron poor. And more reactive dienes will be electron rich because it's using its HOMO, right? So that's the kind of key underlying logic. And then you could easily determine what's what here, right? So now if we look at the groups, first you got to find a base point to start comparing all the molecules. In this case, it's all the alkenes, right? Alkene here, here, and here, right?
Mhm.
So now we could kind of compare what's.
But you're always
what's
looking for
kind
the
of-
alkenes.
What? Yeah, so for dienophiles, right, the main group for a dienophile is the alkenes, and anything else on it is usually electron withdrawing or whatever R groups are here. But the main central group in the Diels-Alder.
For the alkenes in each dienophile.
So let's erase this. Are you guys in the chat following? Just gotta make sure.
Yes.
Okay, cool. So now we could start kind of rating them, like what other kind of similarities do they have is you could say two of them have CH3 groups, right? So if we want to just compare, let's also label them so it's easier to refer to these, A, B, C, and D, right? So look, we can kind of compare B and D first because they're the most similar in structure. They both have an alkene with a CH3 group on one side, right? The other group is different, and then we can kind of determine what effect that group has on it.
You said
right?
B and D?
Yeah, B and D.
Okay.
Right. So B versus D, right? Which one is more electron poor?
B.
B?
Yeah.
Okay. So Serena says D, you say B, right? So now let's look at what's happening, right? This is a CH3 group. Well, let's forget one side of the CH3 group, right? Because that's all same. So this is a CH3 group on this side, and then the other one, this different side is a, what is it? It's a acetyl group. Like this, right?
Mhm.
So if you guys remember from Orgo 1, alkyl groups, there's a property called hyperconjugation, which is essentially the sigma orbitals here, right? They can donate electron density into p orbitals, right? Or yes, yeah, it is technically p orbitals, right? And that means it's not as strong as, you know, like a lone pair or like a you know, like a heteroatom with a lone pair on it donating into it, right? But you know, it does donate some electron density to an alkene, right? So
Mhm.
what we consider alkyl groups are as weak electron donating groups. So this is technically electron donating group, right? It's a very weak one, but it is, right? It's not withdrawing any
I
sort of.
don't get that, the whole electron donating.
So like I said, and this is better explained in the later chapter, but for the most part, electron donating groups are pushing electron density into somewhere, wherever, in this case, it's alkene. In some cases, it might be the aromatic rings, right? Or, you know, any other sort of molecule you have.
Single bonds do this, you said?
Yeah, so this is a property called hyperconjugation. If you want to look it up, right? Should have been covered in Orgo 1, right? But alkyl groups do this, right? So this could be an ethyl group for all you know, right? Like isopropyl group, right? Doesn't matter. If it's some sort of R group or alkyl group, it's donating its electron density via this effect, right? And it's a very weak donation effect, but it's still pushing electron density into that alkene. So is that making that electron rich or electron poor?
Electron density, it's gonna make it electron rich
Yeah. So this is a weak electron
Into-
donating group, and then
into alkenes, and you said aromatic rings.
you should, I mean, to make it more general, into any place that can accept electron density. So it's not limited to alkenes. This can happen. Anything that has a p orbital. You saw it in carbocations, right? The stability of carbocations, primary, right, versus secondary versus tertiary.
Yeah.
Right. The reason why tertiary are so stable is because the more R groups you have, the better your effective hyperconjugation. And this is an empty p orbital,
Mhm.
right? So instead of like alkene, you could write p orbital. P orbital here is part of this pi bond, right?
Mhm.
So here we have a acetyl group. Now what's happening here, right? This is an electron withdrawing group, because what could happen here is you could draw a resonance form, right? That essentially this double bond, because this is an oxygen too, it's a heteroatom. Oxygen is electronegative. I mean, has kind of answered my question here, but does oxygen want electrons or does it not want electrons compared to carbon?
Oxygen wants electrons.
Wants electrons. So this, you know, oxygen carbon double bond, you could always consider a polar bond that oxygen is pulling, like it's partially negative, right? So you could draw this resonance form, right? And what's this showing is that this electron density is now leaving this alkene, right? I'm going to go into more detail when we get into chapter 18. So like, because there's a gigantic table and a lot of people try memorizing it, but if you just look at them quickly, you could easily see what's going to be electron donating and what's going to be electron withdrawing, right? That's going to be very important for aromatic reactions, but it's useful for any sort of thing to understand what is donating density and what is removing it, right? So in this case, the double bond is conjugated here and it's withdrawing electron density. So does that make this electron poor or electron rich?
Electron poor.
Right, because its electron density is leaving the alkene, right? So between B and D, which one would you expect to be more reactive? Which I asked
B.
before. What?
A.
D, right?
Wait, D?
Because remember I said in this case, more reactive means it's more electron poor, right?
Oh,
So,
yeah.
so for now, on the side, you know, you could put, what do we say? B is going to be less than D, right? Now let's look at the kind of rest of the examples. Now we could kind of also compare A and D, right? A versus D, they both have these acetyl like carbonyl groups, but A has two carbonyl groups, right, attached to this alkene, right? So it has electron density going out this way, right? And it has electron density can also go out this way. So it has two electron withdrawing groups. So compared to A and D, which one would you expect to be more electron poor?
A.
So that would make it more or less reactive than D?
A is more reactive.
Okay, so now we could put A here, but now the thing is, the last one remaining, right? It could technically go in between some of them. We gotta look at what's happening, right? So this has the
Wait, can we
amine.
just take a pause? I just have to process what the
Yeah,
information
no, no
was.
worries. I
Okay.
do have to go in 5 minutes, so
Okay.
this is the last question we're gonna be doing.
You said, okay, I'm just gonna go over my notes again. Okay, I was confused with the whole B and D thing. I like, why is, you said D is more reactive
Yeah,
because it's more electron poor.
right. Because it has an electron withdrawing group on it, right? This is all what it comes down to is how many electron withdrawing groups on them are on it and which ones are more powerful than the others, right? So B versus D, we showed that this only has alkyl groups. Those are
Okay.
donating electron density. This has one alkyl group, but it has one electron withdrawing group.
Okay,
So-
and this is more electron poor than D.
Because it has two carbonyls next to the alkene, right? So if we drew this
Yeah.
alkene looking like this, you'll see this is one alkene, and this is the other, right? And you could close off the rings, but essentially you have two groups now compared to one here,
Mm-hmm.
right? So that by definition, qualitatively analyzing this, A has to be more reactive because it's more
Mhm.
electron poor.
Okay, got
So
it.
now the last one remaining, and this is what I think you were asking your question, right? Where you have kind of difficulty understanding this, right? Because you
Which is-
probably think oxygen, right? I'm assuming this is probably your issue. Oxygen is more electronegative, so you think that it's going to be withdrawing electron density. Was that your issue with this?
Exactly, yes.
Yeah. So the reason why it's not is because having a lone pair, right, is more powerful than any induction effect, right? So the way it would be withdrawing electron density, right? You're right in terms of just looking at it, right? That oxygen versus carbon, right? Oxygen is more electronegative. Why wouldn't it want electrons, right? In this case, right, in the inductive effect is just not as strong as it giving its electrons in this way. So whenever you have a lone pair, so this is called an allylic lone pair, right? Right, so you have a heteroatom, or you could see a carbanion like this, right? Those are always donating in, right? They're resonating with the thing, but they're never withdrawing, right? It's additional electron density, right? Because the main, think about this, the main way is that lone pairs want to delocalize, right? So it doesn't matter how electronegative oxygen is, right? That lone pair wants to move around as much as the molecule as it can, right? Because that's what's going to make it more stable. If it's sitting at oxygen all the time, it's going to make it very unstable, but it has an opportunity to move somewhere, delocalizing.
But then what about for that one? Doesn't that oxygen have lone pairs as well?
But it's with, no, but
No, isn't that one, sorry, isn't that that lone pair, isn't it already in the p orbital because it has a double bond?
For which one?
The D, isn't the
Well, so on
oxygen?
D, it's not an allylic lone pair. What's connected to the alkene is another double bond, right?
Yeah,
that's-
that was what I was trying to
So
say.
then the oxygen, right, is, oxygen, like you could draw the resonance structure of a carbonyl like this, right? So this is maybe easier to see that now essentially what we have next to a double bond is a positive charge. And that's why it's withdrawing electron density all the way this way, right? Like I said, when we get to 18, I'm going to go over this again.
I'm gonna simplify it. Just tell me
Yeah.
if this theory works.
Yeah.
This works out as electron donating group because
Mhm.
it's connected to a sigma bond, and this one can't because it's a pi bond.
Yeah.
So that theory works.
I mean, this is because it's a lone pair next to a pi bond. This is because it's a pi bond next to a pi bond. So pi
Okay.
bonds will resonate, but if it's outside the group, it's pulling away density. If it's a lone pair next to it, right, the lone pair is pushing in, giving more electron density, right? So that's why the main thing is that the inductive effect of the oxygen atom itself is not as strong as its lone pair wanting to delocalize. And that's why whenever you see OR groups, you'll see them, or OH groups, right?
Mhm.
They are electron donating groups. And we're going to see this for sure when we get to aromatic systems, because it's very important in elimination addition and SNAR type reactions. And even like NH two amine groups, right? Those will be electron donating, right? These are all sorts of electron donating groups because despite them being slightly more electronegative, right? Electrons want to delocalize because they want to be more stable, right?
Okay.
So that's why it's not an electron withdrawing group. And so if this is a very powerful electron donating group, because this is a lone pair compared to just hyperconjugation, right? Would that make it more reactive than B or less reactive? Or I should say, is it going to be more electron rich or less electron rich?
Think more.
More electron rich, right? Because this is an MEO, like a OME group, right? So that's a full-on lone pair coming in there. So if it's more electron rich, is it going to be less reactive or more reactive?
Less reactive.
Less reactive. And there you have your order. Which is that C, right? So I'll go over electron withdrawing and donating groups again tomorrow. Anyways, I have to join my group meeting here on Zoom, but yeah, hopefully that cleared that up. Just be careful if you get a question like this, because this is just for Dienophiles.
Which exam is this?
2019 RS, right? So if the
2019 RS,
yeah,
like,
it's in the Orgo 2 folder. You'll see it.
Thank you so much, Sharon.
Yeah, no worries.
Have a
Just
good day.
like this logic works for Dienophiles, but literally the exact opposite is true for Di. So just read your question properly. That's a lot of people like they'll do these examples and they'll be like, oh, I did what you said, and I was like, did you read the question? And then they'll be like, oh shit. Okay, so I'm gonna stop the recording and yeah, we'll see whoever comes tomorrow.
Thank you.